All right, let's talk about solving logarithmic functions. You have to understand what the theorem says. So the theorem, which remember in geometry, you learn what a theorem was. A theorem was that you have to solve it. So a theorem means you have to solve it or prove it, I should say. So that was a little bit of geometry there. So we're going to look at solving logarithmic functions. And so here's kind of what we know already. We are trying to say, okay, well, if b is greater than 0 and b is not equal to 1, then the log base b of, let's say, some x1 is equal to some log base b of x sub 2. Then, oh, then we can say that if and only if x1 is equal to x sub 2. So the theorem of this, of equality of logarithms, and I don't know if you remember this or not, but this is called the property of equality of, let's just say, log or logs. So this is the property of equality of logs. So equality means equal, and this is saying if b is greater than 0, but b is not 1, we can say that, okay, we have the same bases. We can say that the x1 is equal to x2. If these are different bases, then we cannot do this. So we can't do this with different bases. So let's go through a couple examples of solving. Okay, so here's some examples here. Let's kind of try a little bit more easy one, maybe. Let's do log of x squared plus 16 is equal to log of 80. So here we go. Now, just to make sure that you understand this, when it says log, it's automatically base is 10. Remember, logs are base 10. So if it's just written as a log, it's base 10. Just to kind of, hopefully that makes it a little bit easier. So we have log base 10. So that means that these are equal. So that means you're going to take this and you're going to equal it to that. Since these are the same bases, so same base, same bases, so that's the same and that's the same, and they have an equal sign, you're going to take the stuff that's inside instead of equal. That's kind of what this property is saying. I don't know if you see that or not, but this is kind of like the x1 and x2 is that. All right, so we're going to set these equal to each other. So we're going to go x squared plus 16 equals 80. Now, this is pretty much just review. This is just a quadratic. Now, you have these methods. So move everything equal to 1, 0. Do you have to do that? No, you're going to have x squared. So why don't we subtract 16 to both sides and move this x squared a little bit closer? 80 minus 16, if you believe it's 64. Now, if you remember how to take a square away, you're going to take the square root of both sides. That's going to give you x equals, remember, plus or minus, I think that's 8. All right, now we have to check for extraneous answers or maybe solutions in this case. Extraneous. Extraneous. What happens is that, remember that the domain of log is, the domain of log is 0 to infinity. So this right here has two answers. This has 8 and negative 8. But according to our definition, or domain, I should say, our domain of a logarithm, that you can't have anything negative. So we're going to say negative 8 is gone because there's a domain issue here. So this is a domain let's say, maybe call it issue. Okay, so hopefully that makes a little bit more sense with these. Does it happen a lot? Quite frequently, especially with quadratics. You have to be careful. All right, kind of going over this like this. So this is kind of going that way. So let's do some more here. Let's do this example. Let's do log base 3 of 3x minus 5 is equal to log base 3 of x plus 7. Okay, check for when you're solving these. So when solving, so you're going to solve, you're going to check if the bases are the same. So bases are same. Okay, and it looks like it's an equal, so that's a good indicator too. All right, according to our theorem that we just had, this is your x1, this is your x2. Going back to that theorem, same bases, they're equal. We're going to set these equal to each other. So that's going to be 3x minus 5 equals x plus 7. Now, this is just pretty much simple solving an equation. So however you want to solve this, subtract x to both sides. I'm actually going to add 5 as well. That takes care of that. That takes care of that. I have 2x on this side, and I do believe that's 12. And divide by 2, and x equals 6. Okay. Now, just check. That's positive. We're good to go. So domain, remember the domain of a log of log. So that's from 0 to infinity. That's positive, so we're good to go. Hope that made a little bit more sense with that one. All right, so let's try this one. What if we had log base 5 of 27 equals some value y? Now, you're probably thinking, well, we're not going to set these equal to each other. We don't have two logs on both sides. That's fine. That works for that. But this looks like, well, we want to get the value of y. So we're still going to solve, but we can actually just do a simple conversion. Yeah, convert to exponential. So remember, here's our base. So it's going to be 5 to the y and equal to 27. Kind of do this little loop. So this is 5 base to the y equals 27. That is good. Is there anything else you can do? Well, there's not a whole lot we can do because we kind of almost made it worse, so to speak, because we don't know what y is. However, if you put this in your calculator, if we had base 5, we can't put this in our calculator because we're not base 10. Later, you will do that. If you put this in your calculator, you can get an answer. This is just an alternate way of saying, hey, I can do it the exponential way. Maybe this is probably your answer if you put this into a calculator because this part equals y. So you can do this in a calculator later. It's another method of logarithms, but we will get there later in another video probably. So let's do something else. So this is all you can do for this. All right. Why don't we try something a little bit easier, maybe? So what if we went log of 7, maybe up to y equals -2. It's a terrible looking y. All right, so we don't know what y is. We can figure it out though, but it looks like we're going to have to change this to exponential. So let's go to exponential and go from there. So remember, our base is 7. So it's going to be 7 to the -2 power and equal to y. All right, we can do this. We can do this. So here we go. Remember that this is 7 to the -2. I'm hoping that you remember from your exponent rules that if I take 7 over 2 and over 1, and I want to make it positive, I'm going to flip it. So it's going to become 1, and then this becomes positive, right? So you're going to flip this, and flip this, and that's going to make it positive. Now, 7 squared is 1 over 49, and that's your answer for that one. Okay? Now, remember, this is like the rule of exponents. You might want to go to the rules of exponents for that one. It's always nice to kind of see those exponents. Okay, let's go to a different base. Different base now. Now, this is called natural log, or logarithmus naturalis is actually Latin. So that's Latin for this. So if you want to, this is called a natural log. And it's Latin. You want to look it up. It is a Latin word. Okay. Natural log, logarithmic naturalist. That's kind of what the Latin part of this is called. I won't put that. That's not really that important. You can look it up if you like. So ln is another way of saying, okay, I have y to the ln of some x. Now, if you look at the graph of this, this looks like a logarithm. This looks like a logarithm. So it's going to intersect at 1, 0. So the natural log of 0 is 1. So the natural log of 0 is 1. Hope that made a little bit more sense there. If you want to check the work there, you can always do that on a calculator just to kind of make that happen. But just take my word for it. All right. Actually, I made a boo-boo. Let's back up. This is actually 0. Let's make it back up. I was thinking the log of 1. The log of 1. If you put that on your calculator, the log of 1 is actually 0. Okay, so this one right here, you can't do it. It does not exist. I'm going to back up here a little bit. It does not exist. Don't do that mistake. However, if you put 1 for x, the output gives you a 0. So that's why you have an intersection here. So this is x, comma, y. So the natural log of 0 is undefined. The natural log of 1 is 0. Don't make that mistake like I did. So if you actually plug in some more values, you get to kind of see something happen. So 2, 3, 4, 5, it's actually going to kind of do this for the logarithm, for the ln. And this is that natural log. It's that. All right. So that's the natural log. What I want to now do is let's look at e. So let's look at the other base. It's called a e. And I don't know if you remember this, but e is an irrational number, so it isn't irrational. And it's about 2.71828. Keeps on going. It's an irrational number. If you were to graph this, so if e to the 0 or e to the 1, e to the 1 is just e. It's just that. However, e to the 0, if you put that into your calculator, is just 1. So that tells me, okay, if I go to my graph up here, remember here's your y, here's your x. If I put in a 0, I get a 1. If I put in a 1, I get the e, which is about right there. So if you actually plug in some more letters, actually plug in some more x's, you would actually get something that looks like this. So this is e to the x. And if you remember anything about lines, y equals x is actually the reflexive of these two graphs. So if you were to kind of draw this graph and reflect it over this line, you would see that that should be the same. The only thing that would differ is the points from here to here. This point right here is at 0, 1, by the way. It just reversed. So that's kind of what we also need to pick up from these, that natural log and e, or what we call inverses. They are inverses of each other. So let's do a couple problems that maybe facilitate that information. And the more you do of these, the better you're going to get at. But let's start a little bit simple. Okay, so let's do maybe e to the example. Let's do ln of -2n plus 1 equals 8. So let's try this one. Now, we're probably thinking, okay, how do I interpret this? Okay, just remember that these are inverses. E and natural log are inverses. So what you're going to do is say, okay, you're going to think about this. What can I do? Well, what if we put an E right here and put an E here? That means that E is all that junk now. And this E is all that. Well, since E and E is on the same side, so we're just adding E and we're raising that. Look right here. E to the natural log, remember these are inverses, they're actually going to cancel each other out. And if that cancels out, this part right here says, okay, I get to just come down because these two cancel each other out. Now you have e to the 8. Well, you're probably thinking, okay, what do I do now? Well, you're still solving for x here. I don't care what e to the 8 is. So if we were to solve this, subtract 1 to both sides, you have -2x equals e to the 8 minus 1. And keep going here. You're going to divide by -2, divide by -2, the whole thing. You have x equals e to the 8 minus 1, -2. And let me write this a little bit better. So e to the 8 minus 1. Okay. So from that, I'm going to leave it like this. This is called exact. The reason that's exact is because remember, E is an approximation. So remember that E is an approximation. And we want to just leave it as exact answer because that's better to do than put into our approximation. Okay? So let's do some more here. The more you do of these, the better you're going to get out of it. And I'm hoping that is okay. But here we go. Let's do e to the 2x equals 5. Now remember these a little bit. So e in natural logs, remember e and ln of x are inverses of each other. So we have e here. So maybe the best thing to do is, why don't we just take ln of this and ln of that? And rewrite this as ln of e to the 2x, and this is natural log of 5. So you're just going to rewrite this as that. Now remember, you told me that I told you that these are inverses. Well, these are inverses, so those kind of just cancel out, and you bring that 2x down, and this is still natural log of 5. Divide by 2. Divide by 2. X is that guy right there. Now, I would leave it that way because this is an exact. Just leave it like that. You're okay. Hope that this is making a little bit more sense. If it's not, then, like I said, you might have to do a couple more of these. But let's do some more here. So let's do this. Why don't we say e to the 5x times e to the 3 is equal to e to the 15x. Now, what I want to do is decide that this is true or false. Is this a true or false statement? So let's see. We got to think about these. This is kind of a little different now. We're still solving, but we're trying to say, hey, are these two balanced? Do they actually equal each other? And you kind of have to think about this. So we have the same base. So remember, if you have the same base, what do you do with the exponents when you're multiplying? You're going to add the exponents. So you're going to go 5x plus 3. So you're going to go 5x plus 3 equals 15x. Remember, these are the same base. Are these true here? Is that true? This is not going to work because when we're multiplying, we're adding the exponents. So this is false. So just kind of a FYI there, or some kind of information. Just don't try to get confused on that. Don't forget your rules of exponents, by the way. Okay, let's do some more. What if we do ln of e to the, let's do the third power. And I want to simplify. So this one's a simplify. So let's simplify this. A good way to help you out with this is that, remember, this ln is all this guy right there. And you're simplifying this. So if you really want to, you could set this equal to 0, y or anything, and just think about it that way. You don't have to do that. You don't have to make this equal because it does say simplify and not solve. What you could do is just think about, okay, if it just says simplify, I'm not solving really. What I'm doing is just kind of making it to its lowest term. So this is just lowest terms without any other factors. So remember that ln and e are inverses. So these are inverses, so it looks like 3 is your answer. That was not bad. That was not bad at all. All right, do a couple more here. Hopefully this is making a little bit more sense. The more you do of these, the better you're going to get at it. What if we do e to the x equals 1? And I want to make sure that, does that make sense? All right. Well, there's a couple ways of going at this. Remember, we are trying to solve. So we're trying to solve for x. Now you're probably thinking, okay, to what? You're probably there. What value of x makes 1? Now, if you're kind of thinking about this, you know that e to the 0 is 1. So technically, you already have the answer. But what if a person didn't know that? Well, if a person didn't know that, what could they do to help us do this? Well, they're maybe trying this. I have e. Maybe I want to get rid of that, so I'm going to go ln and ln because I know that these are inverses. So these are inverses. That exponent is going to drop down. But you have to deal with the leftovers here, and that's the leftovers there. If you had e1. Now, if you go back to before when we said something about the natural log of 1, and I think the natural log of 1, wasn't it 0? Or was it 1? If you want to go back to this part right here, natural log of 1 is 0. And there you go. So 0. So guess what? X is equal to 0. Now, you know this. To check, go back to your original problem and plug in 0. So e to the 0 is 1, and that's what you set up already up there. But that kind of gives you a little test to kind of say, okay, what am I doing here to kind of balancing this out a little bit? Hopefully that made a little bit more clear. And let's see what else we have to kind of offer you for the moment being. Okay, a couple other properties here. So some properties you might want to look at is, what if we had the log base of 1? And what if we had the log base of b to the b? And we had maybe log base b of b to the k. And let's give you one more. What about, oops, scratch that one. What if you had b to the log base b of, let's say, I don't know, let's say k or x. So these are some properties that you might have to understand, kind of makes your life a little bit easier with logarithms. So these are properties. Properties means they're kind of like statements. So these are kind of almost like, statements or statements or facts, statements. You know what I mean? All right. So if we had log base b of 1, that is 0. Because, remember, b to the 0 is 1. Log base b of b is going to be 1 as well. Because b to the first power is b, obviously. And b to the 0 is 1. The next one, log base b to the b to the k. Well, since these two are the same, the k says I get to be left alone. They kind of almost, I don't want to say cancel out. Then the last one says I have b raised, so this is a raise of this part right here, of b to the k. So these two are the same, but you're saying that b to its b is x. Well, that makes just x. So that kind of makes it so b to some base log base b is just its of part. Okay. Maybe we do maybe a couple examples with this. So maybe we can do a couple examples here. So let's do example. Let's do log of 3 to the 3. Log base 3, that's just like this one, is going to be 1. Let's do one like this. What if I said log of, let's make it 10. Let's make it 10 to the 1 power. Well, log base 10 to the 10 to the 1 power says 1. Okay. Well, that's just a couple of examples on this to kind of make this a little bit easier to comprehend. I'm hoping that this video worked out for a little bit, but we will continue with more properties and some properties of exponents. But as you can see, kind of just going down the list here, there's a lot into this here, and you really need to know the inverses and the natural logs of all this because it makes a lot more sense. So there you go. And kind of go through the domain again of logarithms. Remember that extraneous answer cannot have a negative with logarithms. Look at the domain. And that hopefully gives you a little bit better idea about solving logarithmic functions. All right, stay tuned.